Hi guys, so today we'll try to understand the problem of matrix chain multiplication using dynamic programming. Now, dynamic programming is a technique by which a problem can be optimally solved when divided into subproblems, into smaller subproblems, and each of these subproblems are optimal in themselves. And this property of dynamic programming is known as the optimal substructure property, which states that when you divide a problem into the smaller subproblems, each of those smaller subproblems can be optimally solved. And when we combine these smaller optimal subproblems into the final solution, we would obviously arrive at the final optimal solution for the entire problem. So using dynamic program, if we were to consider solving matrix chain multiplication, there are more than a few ways to do so. We could simply multiply the entire chain of matrices one after the other, and that would give us a very complex solution with a large number of multiplications. Alternatively, we could also use dynamic programming and come up with a solution that is more efficient. So let's dive right in. If you were to multiply, in this example, if you were to multiply the chain of matrices from beginning to end, that is from A1 to A4, we would effectively have 4 times 10 times 3 plus 4 times 3 times 12 plus 4 times 12 times 20, which would give us a total of 1224 multiplications. Now this might not be the optimal solution, so in order to guarantee that we get a better solution, we would use dynamic programming, because if we were to simply solve it using this naive approach, we would it would be very expensive in computing, especially if the matrices are very large. We can alternatively multiply different matrices together first in some strategic order, by placing brackets, maybe like so, and by that we would bring down the number of multiplications significantly. And so our goal here is to find an optimal way to multiply a set of matrices to perform the fewest multiplications possible. So a naive approach to solving excuse me, to solving this problem would be to try every single combination and pick the most optimal one. But this would have a disadvantage because it would be very expensive, as the running time would be of the order of this equation, which we can see if this term dominates, then it is exponential, and we do not want that. So we go for a better approach using dynamic programming. So let's first, the first step is to prove that this problem does actually have the optimal substructure property. So to prove that, let's see what we can do. So let's assume that we have a matrix series from AI to J, and let's say that we have an optimal solution for it. That is, we already have an optimal solution for AI to AJ. Now the solution can be thought of as two parts, that is AI to K and AK plus 1 to J. So we can see the problem in two parts, right? So and both the parts when combined form the optimal solution. But if there was a better way to multiply A of I to K, that is this part, if you were to somehow find a better way to solve to multiply the matrices from AI to AK, then we would have obviously a more optimal solution than the one we already defined. And this actually contradicts our initial claim because we already stated that we have an optimal solution already for AI to AJ. Therefore, by proof of contradiction, we have identified that the problem has optimal substructure property. Now, we know that a matrix series AI to AJ, AI to J can be broken up into AI and AI to K and AK plus 1 to J, right? So now the problem arises that what is this K? We don't know the value of K right now. So we wish to find at which value of K we get the fewest multiplications. So we can have a recursive formula for finding the cost of multiplying of the multiplications. The recursive formula is as follows. The cost of multiplying matrices from I to J, Mij, is Mik plus Mk plus 1j, and that is added with these dimensions P of I minus 1, Pk and Pj. Here Mi to j is the cost of multiplying the matrices from Ai to Aj, and Pi minus 1, Pk, Pj are the matrix dimensions. So let's see an example, and it will be clear what these values actually mean. Suppose we have the matrices from Ai to K, and that after computing becomes a single matrix of order 2 by 3. And then we have the other part, which is AK plus 1 to J, which is again a matrix of order 3 by 4. And let's say that the cost of multiplying this matrix was 100, and this set of matrices was 200. So effectively the number of multiplications would be Mik, which is this, which is the cost of multiplying Ai to AK, which is 100. And then we have Mk plus 1 to J, which is 200, and then Pi minus 1, which is 2, Pk, which is 3, the inner dimension, and Pj is the outer dimension, which is 4. So we would arrive at an answer of 324, which is 324 multiplications would be required. This is just an example to clear for the better understanding of what these notations actually mean, right? So now comes the actual part. Since we don't know what K is, we try the range of K between I and J in this manner, where K can be any value greater than or equal to I, but always less than J. And the minimum value returned would be our solution. So the final recursive formula becomes this one, where we have Mij 0 if I is equal to j, that is if we have a single matrix, then obviously the cost of multiplying it would be 0, and if I and j are not the same, then we would have minimum of k, which is the minimum value of k for which we get the fewest number of the value of k for which we get the minimum multiplications, and we already saw this formula before. So let's see the entire algorithm or the example, this problem with an example. So let's start with these 4 matrices. We have A1 to A4, and the dimensions are 4 by 10, 10 by 3, 3 by 12, and 12 by 20. So we'll just write down these notations over here: P0, P1, P1, P2, P2, P3, P3, P4, so that we can reference them later. And we'll solve this problem by creating a table, and we would write down the multiplication values that we got, so that we arrive at the minimum multiplications, and that would be this value. I'll discuss how we'll fill this table in a few seconds. So the first step would be to fill the table when I is equal to j, and from this recursive formula we already know that if I is equal to j, then the cost would be 0. So for I is equal to 1, j is equal to 1, I is equal to 2, j is equal to 2, and so on. We have this diagonal which is 0, right? So when we have a single matrix, we have there is no cost of multiplying. Next, we would fill the table for a spread of 1. Now what this is that we would fill the values when I is equal to 1, j is equal to 2, when I is equal to 2, j is 3. When I is 3 and j is 4, that is when the difference of I and j is 1. That is what the spread of 1 means, right? So yeah, so the first value that we have in the table to fill is I1 2, this box right here, right? So m of 1 2 would be minimum of k between 1 and 2, and that would be and since here we have k between 1 and 2, k can only have one value, right, which is 1. So for k is equal to 1, we would calculate m of 1 2 as m of I k, which is I is 1 and we have taken k as 1, so m1 1, and then mi plus 1. Let me just show you the formula. And we have m k plus 1 j, so k is 1, so m1 plus 1 and j is 2. And then we have pi minus 1, that is p0, pk is p1, pj is p2. So if we put the values, we would get, because m11 and m22 would be 0, we have 0 plus 0, and then we have p0 is 4, p1 is 10, and p2 is 3. So that would be 120, and we have put that value here, right? So we'll go ahead and fill this diagonal right here. All right, so the next value that we have is m23, and I have written the matrices here for reference. It will be easier for us. So for m23, we would have k between 2 and 3, and again the value of k can only be 2 in this case. So we would effectively have mik, which is m22, mk plus 1 and mk plus 1j, which is 2 plus 1 and 3, and then we have these dimensions. You can refer the formula if you want, it would be easier. And so again, we know that the value for with the cost when I and j are the same is 0, so we have 0 plus 0. And then looking at the dimensions, we have p1, p2 and p3. p1 is 10, p2 is 3, and p3 is 12. So we have an effective value of 360. Then the next value in the diagonal is 3 4. So we would follow the formula, and then with the similar calculation we would arrive at 720. So we have filled these values in. I'm sorry, it's so messy right now. 120, 360 and 720. We have filled these values. Now we would proceed for a spread of 2. Now this would mean that the value of I and j differ by 2. That is, we would go for the position when I is 1 and j is 3, when I is 2 and j is 4. These two, because we know that there are only two values possible in this diagonal. So let's calculate that. In these cases, we would get more k values, and you will see why. For m13, we would have k between 1 and 3. So k can be either 1 or 2, because 1 is less than 3, 2 is less than 3. So let's calculate the cost for each value of k. So when k is 1, applying the formula, we would get a value something like this. I is 1, k is 1, so m11, then m23, and these dimensions. So we would arrive at a value of 840. And now when k is equal to 2, we would have m12, m33, sorry, and these dimensions, and that would amount to 264. Now we see that we have two values, and the minimum value is 264. So we would write this value over here for 1 3, this over here, 264, right? Similarly, we calculate the next value, which is m of 2 and 4, and again k can be either 2 or 3. So for k is equal to 2, we got a value of 1320, and when k is equal to 3, when you apply the formula, you would get 2760, and obviously we get 1320 as the minimum, and so we update our table and we have 1320 over here, right? So we are left with only a single block, that is I when I is 1 and j is 4. So let's uh, have a look at that, and that would mean a spread of 3 because I is 1 and j is 4, so they differ by a value of 3. So over here k can be either 1, 2 or 3, so we need to calculate the cost for each of these three values. So when k is 1, we have the following formula, the following numbers, and we get this cost. And when k is 2, we have 1080. When k is 3, we have 1224. And out of these three values, we have 1224 as the minimum. So we updated that as well in the table. This is our final solution, and the value over here implies or gives us the minimum number of multiplications. So the answer is 1224, right? So we arrived at the minimum number of multiplications, but we do not know how to multiply the matrices yet. I mean, in what order the matrices should be multiplied so that we get the answer as 1224, right? So for that, we'll look at the entire problem as a whole. That is, we'll start with M of 1, 4. That is matrices from A1 to A4. And we saw that for M1, 4, we have we got the minimum value when k was 3, right? We got the minimum when k was 3. So what that implies is that we have to put a parenthesis between 3 and 4, right? So it will be as like this. So we have to multiply a1 to a3 first, and then that would be multiplied with a4. Now again, this a1 to a3 is again a problem in itself. So we would again try to get the value of k for which we had the minimum value. And if you look back for M1, 3, the minimum value was obtained when k was 2. So that implies that we have to put a parenthesis between a2 and a3. So the multiplication would be as follows. We have to multiply a1 and a2 first, then multiply that with a3, and then multiply that with a4. In this case, the order was pretty simple. It was actually a1 into a2 into a3 into a4, but it is not always the case. With different examples, you would arrive at different order, and if you take different examples, it will be easier. You can see that. So let's see an algorithm, and it will be clear that you can try and trace the algorithm for this example, and you would get the same solution. So this function or this program, matrix chain multiplication, takes an array of matrices, a series of matrices. For I is equal to 1 to n, that is in this case for I is equal to 1 to 4, we have M, that is the matrices 1, 1, and 2, 2, 3, 3, 4, 4 would be 0, right? Because we saw that if we have the same matrix, then the cost would be 0. So that is what we're doing here. Now for L is equal to 2 to n, this will be clear in a while. We have L from 2 to 4 in our example. Let's just write the values here. So in that we have another loop, that is I is 1 to n minus L plus 1. N is 4 minus L is 2 plus 1. So that gives us 3, right? So we have L from 1 to 3. 1, 2, 3. And the value of j will be calculated each time. Now this is because we have different spread values. That is, in the first iteration we have the spread value of 1, and then the next time we have 2, and then 3, and so on. So that is why we calculate j every time. So j in the first case would be I plus L minus 1. I in the first case we have is 1, so 1 plus L is 2 minus 1, so that was 2. And over here you can see that I is 1, j is 2, so the spread is 1, right? And over here then we have to Then now it's just simple. We apply the value of k. K is from I to j minus 1, that is 1 to 1. So only one value would be considered in this case. And then this is the formula that we saw it previously. And yes, over here we initialize the value to in some, I've written infinity here, but it is actually some very large value. And then if we find that obviously we'll get the value of q, which is the cost, something less than this infinity value. So then if q is less than m of ij, then we would update the value in the table, and then the k value would be returned or stored in some in a different array. The next time, this was for I is equal to 1 to 3 and j was 2, right? Then I would be incremented to 2. J would again be calculated as 2 plus 2 minus 1, that is 3. So 2 and 3. Similarly, we would have 3 and 4. So that is the first iteration with a spread of 1. And after this, we would come out of this loop and the value of L would be incremented. So L would be 3. And when L is 3, we would have again I from 1 to this value. This would be different because our L was different, and then J would be calculated again. So if you trace the entire program, you would arrive at the solution that we got, which was 1, 2, 2, 4, and A1, A2 would be multiplied first, then with A3, and then with A4. So that's it for this video, guys. I hope I was able to clarify this concept, and any feedback would be appreciated on the video. So just let me know what you thought. Thank you.